Hello everyone. Today we will discuss about the World Reference Base for Soil Resources, an international soil classification system that was created by the United Nations. And this specific system is quite complete and interesting because it considers the best and specific properties of the national systems around the world to create an international system that could be useful to classify soils around the world. So it's quite complete and interesting. It's always being updated as the other systems too, but considering improvements from any national system around the world. It also received contributions for soil scientists from all nations. So because of this, it's one of the systems that could be more easily and faster updated than the others. The soil classification according to the WRB, the World Reference Base for Soil Resources, has only two levels. The first level is considered the reference soil group, or just RSG, and we have 32 RSG in WRB system. And at the second level, we have the qualifiers that can be principal or supplementary qualifiers. These two levels, in comparison to the 8 levels in soil taxonomy, makes the classification according to WRB much more easier in some way that you don't need to consider several levels or classes to classify the soil, but at the same time we have a lot of qualifiers that can be applied to each RSG, and because of this, sometimes the classification, the name of the soil according to the classification could be a little extensive or even huge in some cases. We will check this in the next slides, but this qualifiers, they will have an important and vital role in the soil classification because it will be very informative to understand all soil properties and also understand very well the soil genesis. We can consider that the RSG can compose some groups, okay? The first of these groups are those soils that register a thick organic layer or horizon, and in this case we have the histosols. The histosols are basically similar to the histosols in soil taxonomy, soils which register organic matter contributing and influencing all the morphological, physical, chemical properties of the soil. We also have a second group, soils with a significant influence of humans. So we have the anthrosols and technosols, those soils with a high content of artifacts, those artifacts that were produced by agriculture or any other kind of use. These soils comprise the anthrosols and technosols. I like very much the concept of anthrosols and technosols in WRB because in this case we consider that humans are part of the soil formation factors. The humans, they are one of the soil formation factors and they influence and create soil. We have a 30 group, soils with a strong limitation to root growing. So we have the permafrost affected soils, the cryosols, soils affected by a layer or a horizon with very low temperature, Some of these soils, they have ice on some of the sections. This could avoid root growing, but the permafrost is very low temperature by itself. It's also something that avoids or at least reduce root growing. We have some soils that are really thin and or possess a high content of coarse fragments. These soils are called leptosols. Also, we can find some soils with a high content of sodium, exchangeable sodium, and we call these soils as solonets. We know that the high content of sodium, especially exchangeable sodium, could induce an intense clay migration, creating an abrupt change of physical and chemical soil properties between horizons, and because of this we can reduce root growing and water penetration. We also can find some soils that are affected by intense shrinking and swelling. They are called vertisols. These soils are rich in clay and high activity clay, and because of this, this could avoid root growing and also some other physical problems. We also have some soils with a high concentration of salts, especially soluble salts, salts that are more soluble than gypsum. They are called solonchaks. These soils also can register some physical problems, especially avoid root growing, because these salts also could induce or express some clay migration and also affect the chemical and water balance between soil and plants. We also have some soils that has one specific or particular iron aluminum chemistry. Some of them has this particular chemistry because they are affected by groundwater. So the water table fluctuation or tidal water or underwater soils, these kind of conditions are related to the glacials, soils that are deeply affected by water that migrates from the deepest horizons to the surface. We have some soils that has a particular iron and aluminum chemistry because they have a deep complex organic and metal complexes that are formed by organic matter or low crystalline minerals. In this case, we have the endosols. We also have some soils that has a deep connection between organic matter and some metals. But in this case, this deep connection induce clay migration and induce aluminum and iron migration from the surface horizon to deepest horizons. This is the case of the pozols. We also have some soils that express concentration of iron as nodules and concretions, a high percentage of features and bodies that are cemented by iron, and of course this express some past reducing conditions, but reducing conditions that change to very well drained conditions that induced concentration of iron. This is the case of the plintosols. We have also some soils that express some stagnant water, some perched water table, but this perched water table is induced by an abrupt textural difference between the surface and subsurface horizons. This is the case of planosols. We have some soils that only express stagnant water or a perched water table. This is the case of stagnosols. We have some soils that express a shiny surfaces like clay skins, clay features. They register low activity clays and they have a strong grade. This is the case of needy soils. And we have some soils that express a deep and wafering and leaching. In this case, we know the soils as ferro soils. We also have soils that are enriched in soil organic matter in the top soils. So soils that possess a very high content of soil organic matter at surface. These soils that register high soil organic matter content plus presence and abundance of secondary carbonates, they are called Chernozans. The soils that register median or at least lower soil organic matter content than the Chernozans and also secondary carbonates, they are called castanosans. Soils that register a low or median soil organic matter content, dark colors, but they don't register secondary carbonates but a high base saturation, they are called phaeozans. And those soils that register a dark color because of low or median soil organic carbon content, no secondary carbonates, and a low base saturation, they are called umber soils. We have also a sixth group of soils that express some accumulation of non-saline substances. For example, some soils that present accumulation and or cementation by secondary silica. They are called dirty soils. Some soils that express accumulation and or cementation by secondary gypsum. They are called gypsy soils. Soils that express the presence of secondary carbonates, but in this case, low organic carbon content, they are called calcium soils. We also have some soils that are enriched in clay at subsurface horizon. Some of these soils, they present an interfiguring of coarse and fine horizons with some irregular transitions, irregular boundaries between these two horizons. They are called ready soils. Some soils that present low activity clays and low base saturation, they are called aqueous soils. Soils that register low activity clays and high base saturation, they are called lixisols. Soils. Soils that register high activity clays and low base saturation, adisols. Soils that register high activity clays and high base saturation, they are called luvisols. About this group, it's quite interesting because you should consider that in soil taxonomy we have just two orders for this. We have the alphisols and the ultisols, and for WRB we have 5RSG because we consider that we can register differences of low and high activity clays and low and high base saturation, and also some specific morphological features. We also register a last group that express an incipient wafering pedogenesis level. That is the group that express soils that are at least they register a weak grade. Some of them are moderator developed. They are called cambisols. They express at least a B horizon and some pedalization. We have some soils that express a lot of layers and a strong grade and a strong structure related to this stratificated sediments, these layers. They are called fluvisols. They are strongly related to fluvial, alluvial, and colluvial sediments. We have some soils that register a sandy texture, and because of this sandy texture, they don't register any kind of structure development. They are called arenosols. And the last one, those soils that don't register a significant profile development, they don't register a B horizon, they don't have any specific soil process that create those soils, they don't have any specific property or diagnostic horizon that helps you to classify as any other of the RSG possibles. So we call these soils as regular soils. The regular soil should be your last option in soil classification, considering that that specific soil profile cannot fit the criteria and the properties of any of the other RSG. Just to consider that we have the 32 reference soil groups at the first level, we have the qualifiers as the second level. And as I said, we have in some cases a large number of possibilities that can be fitted and added to soil classification. Just as an example, in this case, let's say that we classify at the field specific soil as a solonets because it registers specific soil properties and a specific diagnostic horizon, that's the metric horizon. Okay, in this case we call that soil as a solonets. Now we need to check which qualifiers could be fitted, could be inserted, that could be added to soil classification according to the column of principal qualifiers and the supplementary qualifiers. The principal qualifiers are added before the name of the reference soil group, and we add them according to this specific list. Okay, the first uh, the first qualifiers, they are more important or they have a precedence to soil classification. So for example, let's say that I check if this specific soil profile also fit the criteria for abruptic, and this soil did not fit the abrupt qualifier, but it fits the gleic qualifier. So I will add gleic to the name. And I check the stagnic, no, molic, no, salic, no, but gypsic, yes. So in this case, how should I write the name of this specific soil? I should include gleic very close to the name and gypsic far from the name. Okay, so all these qualifiers, the qualifiers that are on the top of the list, they should be very close to the reference soil group, and those that are in the end of the list, they should be far. So which higher, how higher is the qualifier means that it will be far or close or related to the reference soil group. Okay, just as a second example, if we have an abruptic and gleic solonets, the name should be gleic abrupt solonets because abrupt should be close to the name solonets. Okay, the supplementary qualifiers, they are always added between brands and we use a comma between them. The supplementary qualifiers, they in general starts with the texture, for example, arenik, claytic, loamic, siltic, and then we use the others. And the supplementary qualifiers, they are organized according to the alphabet. Okay, so in this case, we don't need to worry about this. We just add the list according to what appears here, according to an alphabetic order. Okay, always between brands and using comma between them. So principal qualifiers before the RSG, supplementary qualifiers after the RSG, between brands and using comma between them. But we also can add more information when we use some prefixes that could be added to the principal and supplementary qualifiers. So both qualifiers could be added according to the occurrence of each of these qualifiers. So for example, if we have one specific diagnostic horizon or diagnostic property that occurs between 0 and 50 centimeters. So let's say that one specific horizon starts, for example, the gypsic horizon starts between 0 and 30. So at 30 centimeters, we can register the gypsic horizon, but this gypsic horizon ends before 50. So ends around 40, 45. Okay, so between 10 and 40 centimeters, we can register the gypsic horizon. In this case, the gypsic horizon receives the epi term. So we have a epigypsic because the gypsic horizon starts between 0 and ends before 50. So any diagnostic property or diagnostic horizon that starts at 0 or after 0 and ends at 50 or before 50 receives the term epi. All the qualifiers that starts at 50 or after 50 and ends at 100 or before 100 centimeters, they receive the term endo. So for example, if we have glyc properties that starts at 50 but ends before 100, for example, 90 or 80 centimeters, so it's an endoglyc. Okay, so epi at 0 or after 0 and ends at 50 or before 50. Endo starts at 50 or after 50 and ends at 100 or before 100. We also have the term amphi. The term amphi, it's used to qualifiers or diagnostic horizons that starts after 0 and they don't start at 0 and they ends after 50 but before 100. So all these examples, you can see that, for example, this specific one starts at 5 centimeters and ends at 95 centimeters. So it starts after 0 and ends before 100. Amphi. We also have the term ano. The term ano, it's used to those diagnostic horizons or diagnostic properties and apply it to qualifiers that starts at 0 and ends after 50 but before 100. So it's similar to the amphi, but in this case we need that specific diagnostic horizon or diagnostic property starts at 0. So it starts at 0 and ends after 50 but before 100. We also have the term kato, and the term kato, it's used to those diagnostic horizons or diagnostic properties that starts after 0 but before 50 and ends at 100 or after 100. So kato means that they start after 0 but before 100 and they end at 100 or after 100. And we also have the term panto. Panto, it's when you have the total thickness of the soil fulfilling a specific diagnostic horizon or a diagnostic property. So between 0 and 100, or even after 100, we fit one specific diagnostic property or diagnostic horizon. And as I said, you can edit this soil classification according to these terms. So the same soil profile that I classify it as a gypsic, gleic, solonets, claytic, ochric, raptic, I can just add now that I have a epigypsic, so means that the gypsum horizon starts at 0 or before 100 and ends before 50, I'm sorry, starts at 0 or starts before 100, before 50 and ends before 50 or at 50. We have an endogleic, we have a gleic properties that starts at 50 or after 50, but they end at 100 or before 100. We have a pantocleic, means that all the soil profile register clay texture. We have the ochric that express a low content of organic carbon in the surface and the first centimeters of the soil profile. In this case, we don't add ano, canto, panto, amphi, anything. But we have here anoraptic. Raptic is related to lithic discontinuities, and in this case we have lithic discontinuities that starts at 0 and ends after 50 but ends before 100. So we can just add these terms to improve the information, improve the soil classification according to WRB. It's not an obligation, it's optional to add this information, but of course adds a lot of information that could be useful to you. I think that this could be the hardest part to classify soils according to WRB, and a lot of people has problems with this, but you don't need to worry. You just need to use if you want to use, if you feel comfortable to use them. But of course, they add a valuable information to WRB soil classification.